All right, so ideal gas law is PV equals nRT. And then there are derivatives of this where D equals MP over RT with density and molar mass. And we also can convert number of moles, mass over molar mass. So the lab you did yesterday includes magnesium metal that reacted with hydrochloric acid, which gave you magnesium chloride, that's the solution, and the hydrogen gas were the bubbles. So that's a 1:2 ratio. So you're going to use number of moles to find the number of moles of magnesium. Then you can obviously find number of moles of hydrogen using stoichiometry. And then you can plug into PV equals nRT. Since you have temperature, you're assuming pressure is going to be 1 atm. That's your sea level pressure. And then volume is whatever you measured. But keep in mind, 1,000 milliliters is a liter. So if you got 80 mils, then that means 0.08 liters of volume, okay? Now, the other thing that you have to calculate when you're calculating this stuff with the gas collected over water, which is exactly what you did, is this idea of gas collected over water, which I wrote down the formulas for you, if you remember this formula. So this means total pressure, atmospheric. This is, in this case, it's the hydrogen gas you're collecting, and this is a given. Okay, so depending on temperature, water has a certain partial pressure that you'll take into account, and you will use that to find the pressure of the gas, and that again, you're using the atmospheric pressure. So what that means is if I'm going to assume that atmospheric pressure is 760 millimeter mercury or 1 atm, whichever one you want to use, then I'm going to say partial pressure of hydrogen is equal to this, and then plus the partial pressure of water. Now, how do I calculate this? This is not a calculation. This is a table where it's given to you. So the partial pressure of water is dependent upon temperature. So maybe it's like 24 millimeter mercury for 22 degrees Celsius, something like that. Once you plug that in, you'll find the partial pressure of hydrogen. This you need to just Google depending on your temperature. You just put partial pressure of water vapor at whatever temperature you had for your water. Now, the partial pressure of hydrogen gas will be obviously this total pressure minus the partial pressure you found of your water, and that's going to be the pressure of hydrogen. So then you can plug into PV equals nRT to solve R to see if is R really 0.0821. So that was the whole point to the lab. You'll do the calculations with that and just give me calculations, nothing else. You don't need to give me anything from the packet. Just give me the calculations on a separate piece of paper, and you can turn that in by Thursday, because it's just one little calculation that you have to do. I don't want anything else for the lab. Okay, so you can do that. You can pause this right now. You can go ahead and get a separate piece of paper, solve, and then turn that into me tomorrow when we're in class. Now, Dalton's law and the partial pressure gases collected over water. So we're going to do just some sample problems of what is going on here. Look at number 1. It says 250 milliliter sample of oxygen gas is collected over water at 25 degrees Celsius and 760 torr pressure. What is the pressure of the dry gas alone, vapor pressure of water at 25 degrees? Right here, this is the given. This is always going to be given. So when we're dealing with partial pressure of ATM, that's this, right? And then we're looking for the partial pressure of oxygen gas plus the partial pressure of water. So the water one is given, so all you do is 760 is equal to partial pressure of oxygen, which is your unknown, plus the 23.8. And then all you do is subtract, and that's it. Now, if we do something like number 2, where we're going to use PV equals nRT plus the gas collected over water. So let's look at it. It says 32 ml sample of hydrogen. So volume is 0.03 liters. It's collected at 20 degrees, so temperature is 293 K. And 750 torr, right? So we're looking at, this is 750 torr of pressure, is not the gas pressure, it's the total pressure. What is the volume? So we're looking for volume at STP, which is, temperature is 273, pressure is 1 atm here, right? And so we're going to find the pressure of the gas, which is just 750 minus 17.5, and then you can divide this by 760 to find atm, so that we have the combined gas law that we're using. And so this is the only extra step that we're doing with the partial pressures of water. Now, what if we're dealing with Dalton's partial pressure? So this is what we're talking about. Let's look at number 4. You have a mixture of gas that has 2 moles of hydrogen, 3 moles of NH3, 4 moles, 5 moles, and the total is 800 torr. Now, what is the partial pressure of each gas? So now you have to think total versus part, right? How many moles do we have? 2 plus 3 plus 4 plus 5, right? That's 14 moles of gas, right? So 14 moles. Hydrogen is 2/14 of that, okay? So when you do the math on this, you just do 2 divided by 14. So that's 0.14. So this is a fraction of that, right? Times 800 would be the partial pressure of hydrogen gas. So hydrogen makes up 114.3 torr of the pressure. Now, how about the other ones? Well, 3 moles of NH3 is, I'm going to write it here, 3 out of 14 times 800, right? And then you get the idea. 4 out of 14 times 800 would be CO2. So this would be NH3. This would be CO2. And then the 5 out of 14 times 800 would be the N2. So this is the idea behind this Dalton's, where P total equals the partial pressure of, in this case, it's NH3 plus the partial pressure of hydrogen plus the partial pressure of carbon dioxide plus the partial pressure of N2. Okay, so ideal gas law and the collected over water in one problem. Here's a good example. So let's read this. The oxygen produced is collected by displacement of water at 22 degrees Celsius. So anytime it says collected by displacement of water, you know you have to use this other formula along with ideal gas law. So that's where that comes in, and it says total pressure. So this is 754 torr. So we know that, and it says water's pressure is 21. So then we're going to find oxygen's partial pressure, and this is 21 torr. So we're going to keep that aside and then read the rest of the problem. The volume is given to you, and we want to know the oxygen. Okay, so we also have temperature. And here, since this was a stoichiometry problem, but I haven't added stoichiometry yet, I'm also going to tell you that number of moles of oxygen is, let's say, oh wait, it's a number. Number of moles of oxygen is also what you need to calculate after. So calculate number of moles. Okay. So let's first calculate the partial pressure of oxygen. Let's find that first. So 754 minus 21 gives you partial pressure of oxygen. So partial pressure of oxygen is equal to just simply 754 minus 21, 733 torr. But remember, we can't have torr in ideal gas law, so I'm going to divide that by 760, and that gives me 0.96 atm. Now, I have pressure, I have volume, I have temperature, plus the 273, right? So this is 295 Kelvin. We already know R. R is a constant. And we are looking for N. So all we're going to do is plug in to PV equals nRT. So we're going to plug in 0.96 atm times 0.65 equals N. R is R. I'm not going to write it out. Times 295. So we're going to do the math on that. 0.96 times 0.65 gives you, this is 0.624 equals 295 times 0.0821, which is 24.22. So 24.22 equals N. So 0.624 divided by 24.22 gives you, so N is equal to 0.0258 moles of oxygen. So this is just an addition, this part right here, to the ideal gas law. When it says, you have to make sure though, it says it's collected by displacement of water. And this temperature of water will always be given to you because that is a constant that doesn't change, its temperature dependent. All right, so let's do one more. Okay, so here's a problem that I want you to solve using both the partial pressure of water and water vapor, gas collected over water, along with one of the PV equals nRT, but it's a derivative because it's asking for density. So this is where you should pause, you should try out the problem, and then come back and solve it with me. So here's what we have. The formula for density is MP over RT. So it's density we're looking for, but we know this hydrogen is collected over water at 20 degrees. So 20 degrees just tells me temperature. R I already know. Pressure is what I'm going to find now. So partial pressure, the total pressure, is equal to the partial pressure of hydrogen gas plus partial pressure of water. The total, it tells me 780. Hydrogen gas is what I'm looking for. And water is given to me right here as 18 torr. Remember, torr and millimeter mercury are the same unit. So now partial pressure of hydrogen gas is 780 minus 18, which is 762. I'm going to divide that by 760, which is going to give me something close to 1. Let's make sure it's exactly 1. 762 divided by 760. Yeah. So 1.002, but we can just use 1. So 20, we're going to add 273 to. Density is what I'm looking for. Now, molar mass, it says hydrogen gas, and hydrogen, remember, is a diatomic. So that's 2 grams per mole. And then times 1 divided by R times 293. So 293 times 0.0821, that gives me 24.06. So 2 divided by 24.06, and I'm going to get density to be 0.083. And what is the unit for density here? It's grams per liter. And hopefully you got that. And on Thursday, we'll do some more problems. and we'll move on to stoichiometry and Graham's law. Have a wonderful day.